If you ever wondered how the world of chips actually work from analog and digital design to IP, AMS, and CAD automation, in this marathon, we are taking you behind the scenes of the global VLSI ecosystem, exploring how various companies, design domains, and technologies all connect to produce a single chip. We will start with the big picture, then deep dive into the job sectors such as digital design, analog and AMS systems, IP characterization, and even the hidden domains of test chips and CAD automation. So stay tuned, stay focused till the end of the episode. Welcome friends, in today's video we are going to discuss about the bird's eye view of the VLSI ecosystem. Bird's eye view means whatever we can see from the top level. Let's begin. Here in this particular video do not require any kind of prerequisite. Absolutely newbie can watch this video. So here this is what I am going to say about the VLSI ecosystem, what companies are there and how they function, how they interact. So here you can see lot of encircled names like fab, chip design house, EDA tool manufacturers, services companies, IP design house, post-silicon validation companies, and there are a lot of arrows going from one direction to another direction. So this means that these things are well interconnected. Okay, so let's begin. We say it is a fab and also we say it is a foundry. What a foundry does. So fabrication house or foundry, it physically fabricates the semiconductor chips from various fabless design houses. It also provides the device level models to the design house or the IP manufacturers. Primarily as a file, they provide tech files, design rule document containing the DRC, also various metal via details, design constraint, the PDKs. So fabrication house, they manufacture the IC on top of the silicon. Let's move on to the next section, IP design house. IP design house is connected to the fab because when you order the PDK from the foundry, you also need the compatible IPs to use in your design, whether you are doing an analog or a digital design, any type of. So IP design house is what they make. They manufacture different type of IPs like analog, digital, mixed signal IPs. Broadly, if it is a digital, it will contain the logic families, high-speed interface IPs. Also a chip needs memory, so there will be memory, flash memory, SRAM memory. Bitcoin IPs are nowadays very much popular also because of the Bitcoin mines. For a chip to be fabricated also IO, PLL sometimes acts as a clock, BCD IPs, networking IPs also needed. Automotive IPs are now in a high tide because the automobiles, they also use a lot of electronic gadgets inside them. So it is kind of hotcake nowadays. IP design houses makes the IPs in a different formats. So either they can supply the soft IPs or the hard IPs. Mostly it is hard IP, or in between there could be a firm IP also. These IP design houses also have a unit who usually makes the one test chip where the different combinations of their IP, whatever they manufacture, are used to check the functionality at the silicon. So they go up to the silicon also. The silicon actually made in the fab, but this is done there also. The next block here is the chip design houses. What they do. So if it is a digital chip, they will make the SoC from RTL to the GDS2. If it is an analog company, they will start their design with the schematic and they will go to layout and finally they stream out to GDS2. The design, if it is a mixed signal, then they will combine both the RTL as well as schematic at the beginning for their digital and the analog block. Combining mixed signal flow will continue up to the GDS2. And also the FPGA companies, they will also design FPGAs. The next companies are EDA tool manufacturer. These manufacturers do, they make the softwares for the various parts of the design process. We cannot do it by hand, so we have to do it by software. Whatever design, say if we make the RTL, we have to write the RTL in some of the softwares and verify them, whatever they are. So broadly categorized, these tools are like verification, synthesis, PNR, physical verification once the layout is done, timing, extraction, layout, DRC tools. If it is an analog, then it will be SPICE, analog layout, analog verification tool. tools. If there are mixed signal designs, they will use the mixed signal verification tools. So these companies, EDA tool manufacturers, these are called also product companies because they sell the software product and they sell software as well as corresponding application engineering services to their client. Next particular set of companies are services companies. So these companies do what? They have a set of manpower of various kinds. It could be verification, it could be analog IP design, it could be layout experts. Okay, so based on the projects, whatever they get from different chip design houses, they sell their manpower to that company, and because we'll keep a reservoir of people who are expertise in different domains, and those people will cater services to the chip design houses for the particular project. Maybe it could be one particular SoC from beginning to end, or it could be some IP design also. So these companies do not make any products, rather their strength is the people who are working there, and they sell their people's expertise to the other companies. Let's move to the next section. So here are some more words for these companies, like they provide skilled manpower to the chip design house, IP design house, post-silicon design house. So post-silicon design is also needed because once the chip comes onto the silicon, people has to test it. Provide project-based design services. Means whatever I just talked about, that one particular IC is designed or the SoC is designed from the beginning to the end. So that will need a dedicated team to work on that. So that is provide the ODC, offshore development center, where say maybe the services company is in a different country and the product company from whom they are working in a different company. So they set up a ODC in the company where the services company are, and that ODC will function only for that particular product company. So this is a kind of ODC model. So the post-silicon validation company. Now summing up all together these things, the chip is designed. When it is done, it goes to the fab, and fab manufactures in silicon. It comes back to the chip design house. So the post-silicon validation companies, it could be inside the chip design company or it could be a separate outside company. So they what will do that once the silicon is made, they will make the test chip. Test chips, they will validate through the physical and electronic verification system. So they will be physically verified and they will be compared to the software testing which has been done before the tape out. And so there are multiple things will be compared as per the stimulus. They will be compared against the statistical simulated values like Monte Carlo or something. Silicon yield is another factor these companies have to analyze. Obviously, when we are making a chip, it will have some frequency, and that particular frequency of operation is also checked there. The chip, because of the process variation, temperature and voltage, there will be various kind of chips and operating conditions. These also will be verified by these companies. And finally, once all the testings are done, so they will generate the silicon report for that particular chip, which we call a test chip. So guys, here the whole bird's eye view has been given to you, and you can see all together different types of companies, how they function and how they interact among each other. So first we will cover VLSI domain from a bird's eye view. Next we explore domains inside digital design. Next we explore domains inside analog design. Next we explore domains inside analog mixed signal design. Next we explore domains inside IP design and characterization. Next we will explore domains inside test chip unit. And finally, we will discuss the common fabric of all the domains, that is CAD automation, that is omnipresent in all of the domains. So this is a very long series containing very high quantity of information. So in today's episode, we will discuss about this and this. So without any further delay, let's begin. VLSI domains bird's eye view. In this slide, you will be introduced to various domains inside the entire VLSI ecosystem. This oval represents the superset of the VLSI domains. Now, let me introduce the subsets one by one. Although I am calling them subsets with respect to the bigger set, but they itself are the domains that were asked in the question. So here is our digital design. The digital design exists for multiple types of chip making technologies such as ASIC, application specific IC, FPGA, field programmable gate array, and SoC, that is system on chip. I will walk you through the digital design flow in upcoming episodes in the Q&A track. Next is the analog design flow. In college, you have came across PLL, op-amp, oscillators, and many more analog circuit operations. This also come as IC. These ICs are designed in the analog design domain. There is a third domain, which is a mixture of both the analog and digital domains. This is called the analog mixed signal domain, also known as AMS domain. This is becoming very popular with recent advancement in technology. You might have heard about ESB, SerDes, MIPI. These are all good examples of AMS design domain. Now, each of the analog or digital design needs building blocks or units with unique functionality. These will be used when we design a very large circuit. Another side is that also whatever designs we make through various VLSI EDA softwares must be realized in actual silicon to observe the on-chip performance. For this, two important needs, there exist two more very important domains in all of the above mentioned domains. The first one is IP design. Here we make unit cells or design blocks. Standard cell is such a famous set of IP collection which every digital design needs. A set of standard cell will contain combinational logic gates, sequential elements, level shifters, and many other important cells needed for the physical design. Analog IP examples are DC-DC, PLL, A to D and D to A converters, any kind of unit memory cell, etc. The next is test chip. The test chip, as the name suggests, is a full functional chip for the design under test. This design can be a digital block, analog block, or AMS block. In other words, a test chip is a miniature prototype of the actual IC in VLSI. This is an actual silicon chip manufactured in fab, that is foundry. This chip is tested in breadboard level and the outcome is compared to the EDA simulation values. Then the comparison details are published as silicon report. So here we are done the bird's eye view. So let's move on. Domains inside digital design. The digital design can be for ASIC, FPGA, or an SoC. In digital design, the design flow often referred to as the RTL to GDS2, as the design starts with the RTL coding and ends up in a GDS2 string. So here goes our entire digital domain. The first is RTL. For RTL coding domain, you need skills like Verilog, VHDL and System Verilog. Your knowledge must be at the expert level and not as per the beginner level. That means you have to know each and every bric-a-brac of the HDLs I have just mentioned and making designs, making complex circuitries with all these languages. The next one is verification. Here, you do the functionality verification using system Verilog assertions, UVM, OVM verification methodologies. So, you need an expert level knowledge on assertions, UVM, OVM, etc. To get the expert level knowledge, you must consider the LRM, that is Language Reference Manual. It's okay if you're learning from a book, but this Language Reference Manual obviously helps you to get the accurate information. One more thing, these languages are continuously updated as per the VLSI industry need and progress. So you must consult the latest LRM and not an old one. Next comes the domain for the DFT, that is Design for Testability. Here you deal with IC design techniques implemented inside the chip to conduct manufacturing tests. For this, you must have skills on software such as Tetramax, DFT compiler, etc. You will come across terminologies such as ATPG, ATE, BIST, MBIST, JTAG, etc. as skill sets for this DFT domain. Till up to this point, we were at the front end. Now we are entering into the back end or physical design, and the domains are PNR, CTS, ECO layout. I have captured them inside one single circle. At the very beginning of physical design, an engineer deals with EDA tools for PNR, that is place and route, clock tree synthesis, that is CTS, layout, and its ECO, that is engineering change order. The physical design engineer translates the tested and verified netlist into layouts. Hence, he or she makes a physical layout which will be fabricated on silicon. So, this stage is termed as physical design. Tools like Encounter or ICC2 you need to learn for this particular stage. Next domain is physical verification. This includes physical layout verification using methods such as design rule check, layout versus schematic, that is LVS, electrical rule check, that is ERC. You need to learn and gain expertise in tools like IC validator, ICV, ARC, that is PERC, IVPS, etc. Once all the verifications are okay, that is no error is found, you can extract the parasitics as PF or SBPF with the help of extraction engine such as StarRC. Then you can run electromigration and IR drop checks, that is EMIR verification. You may need to gain expertise in tools such as RedHawk, Totem, VoltaSpy. Thus, you confirm reliability checks and complete the physical verification of the layout. The next domain is STA, that is static timing analysis. This can be done in pre-layout also, but mostly it is considered as a part of the physical design. To gain expertise in STA, you must develop skills on the STA tools such as prime time, encounter timing system, and Tempest. The next domain is sign-off. This is most crucial and important before the GDS2 is sent out for tape-out, which goes to foundry. Often the engineer working in this domain is referred to as a tape-out engineer. Generally, this is a very senior position with hands-on experience on multiple tape-out. This stage, an engineer must have a sound knowledge of the entire RTL to GDS2 flow. The sign-off tools such as NEC, SEA, IREM, etc. are needed as your skill set. Again, emphasizing that due to the criticality of this position, you can reach only when you have enough experience. This is certainly not for freshers. Now, in large product companies, you may see that separate teams are working on separate domains, as you can see in this slide, but in case of a startup, one person, that is one engineer, may hold the responsibility for more than one domain. So I have made clear all the domains in the digital design, and hence we have reached the end of this particular slide. So let's move on. This is the same menu as of the last episode. We have covered this and this in the last episode. So in today's episode, we will cover this and this. So without any further delay, let's begin. Domains inside analog design. Here, the oval represents the entire analog design domain. Now, when you are in college, you might have been encountered SPICE language through PSpice Student Edition. That knowledge will be very relevant in this analog design domain. In analog electronics, you have come across analog circuits such as op-amp, PLL, oscillators, etc. These type of integrated circuits, that is the ICs, are designed in this particular domain. We start with the schematic design. Now, let me give some background why schematic capture is important in college. When you have learned the SPICE language, to convert a circuit diagram into the SPICE language, you have to mark each node by hand with a particular number. Then you have to use a text editor to write the .cir file. This is good enough for the college level small circuits, their design and analysis. But when we do the large design in the VLSI industry, this is not a very fruitful method. So we need some method which is far more efficient in the industry level analog circuit design. In schematic capture, you have a GUI where you can drag and drop various active and passive circuit elements visually and make the entire connection in point and drag method. Thus, you can do a design block, also known as a design unit. You can save this particular unit in the pre-existing PDK library for reuse at any later time. Also, you can
can use small pre-designed blocks coming with your PDK design library. Once you make a schematic design, you can include all the spice analysis methods and run the simulation directly. Also, you have a choice to export the schematic into spice.cir file and then simulate with your spice tool. To work in the schematic capture, your base of analog electronics must be very strong. Also, you have to learn few more softwares like Cadence Virtuoso and Synopsys Custom Compiler. Both these tools have schematic capture in them. However, you can start using the free software called LTSpice, which has the schematic capture capability. Here in the pre-layout, functionality verification is nothing but analysis with methods like transient, AC, DC or noise analysis. In this stage, you may need to create several test vectors for various combinations of the input pins of your analog design. In analog electronics, generally the test vectors are written using piecewise linear, that is PWL, or pulse vectors. You have to use several measure statements, that is spice commands, to get the required data from the output waveform. Thus, you will tally your input vectors versus the output response of the design under test. Once we are done with the functionality verification, we move on to the layout design. Generally, the unit blocks are done by hand. Then they are put into the PDK library. For a bigger design, the routing engine is used. As compared to the digital counterpart, generally the analog layouts are not such huge size. So, semi-custom or full custom layout techniques are used for case-by-case basis. Both the Virtuoso and the custom compiler have the layout capability. So in a nutshell, you have to learn either of these two tools if you want to work in this particular domain. The physical verification is same as the digital flow. This is because once the layout is ready, we cannot really differentiate it with the layout coming from the digital. In layout, everything is in terms of diffusion region, wells, poly, several metal layers, via interconnect, etc. So the physical verification is done using tools like Calibre DRC, PVS, ICV, etc. The layout is made clean of the DRC and LVS errors. Then the DSPF is extracted using SAR-RC tool. Using this DSPF, EM and IR violations are detected and corresponding rectification is done going back into the layout. We also check the antenna rule check and ERC at this stage. Generally, these are done using the Calibre, PVS and ICV tools. The EMIR are done using custom sim EMIR, Voltasify, etc. You have to learn these tools to work into the physical verification domain. Thus, we conclude the physical verification check. The post-layout functionality check is done to see the impact of the parasitic resistance, capacitance and coupling capacitance coming from the extracted DSPF netlist. The DSPF is simulable by the industry standard PICE tools. They use a method called RCTC back annotation to stitch the parasitics from the DSPF back into the pre-layout schematic netlist. Thus, with the same test vectors from the pre-layout stage, the shift in the behavior of the design under test is observed. As per the percentage of the shift, separate actions are taken case by case basis to ensure that the original intended performance of the design under test is within the permissible change limit. At this stage, industry standard SPICE and PASSPICE or accelerated SPICE tools are used, such as ASPICE, Erlo, Spectre, Custom Sim, HSIM, Fine Sim, Ultra Sim, etc. These industry standard SPICE tools uses the multi-threading or multi-core software technology to deal with the huge design database. We are done with this particular slide, so let's move on. Domains inside AMS design. In recent times, the AMS designs are becoming hugely popular. The scaling down of the technology node below 10 nanometer pushed the semiconductor industry to think with a different approach. Hence, the analog mixed signal designs are getting pulled from the various parts of the semiconductor ecosystem. In analog mixed signal design, both digital block as well as analog block are present. This oval represents the system level design. In AMS, we start with a little bit different approach. We go either top down or bottom up approach. In either approach, we design the blocks with system level modeling with C, C++, Simulink or System Verilog. All of these skill sets are needed to work at this particular level. Next comes the schematic design for the analog blocks. I have already mentioned in detail in the last slide of this particular episode. Here we use tools like Virtuoso or Custom Compiler. The next comes the behavioral design. Now, this is the most important part of the AMS design for you right now. You are well aware that Verilog is used for digital RTL modeling. Similarly, Verilog A is used for the analog behavioral modeling. When we want to use both of them, we have their parent level superset called Verilog AMS. Verilog AMS makes room for both Verilog and Verilog A to work together. It has same additional features to deal with the modern day AMS behavioral modeling. So at this stage, you must have skills like Verilog, System Verilog, Verilog AMS, Verilog A and VHDL AMS, etc. Next, we have the very critical stage, that is the mixed signal verification. Here, we have special kind of simulator pair, that is analog simulator plus digital simulator working together and handshaking for cross-domain signal transaction. In such kind of verification, the analog simulator such as SPICE or Verilog A simulates the analog circuit block. At the same time, the digital simulator such as Verilog or SB simulator simulates the digital block from the entire design. Both the simulations happen concurrently and with the exact same time step and time scale. Whenever needed, handshake happens between the two. One thing to emphasize that at the analog digital boundary, proper A to D or D to A converters have to be properly configured. Thus, transaction between analog signal and digital signal happen without any errors. For this stage, you must have skills on industry standard AMS tools such as Virtuoso AMS, Western ADMS, Custom Sim VCS from the three major EDA tool vendors. Once the netlists are okay, then we go to the PNR and layout. At this stage, the layout is done for the digital and analog parts. You have to learn the AMS layout skills for Virtuoso AMS, Western ADMS and Custom Compiler AMS layout. Once the layout is done, the physical verification is taken care. There we use the DRC or LVS tools such as Caliber DRC, PVS, ICV, etc. We also check for the ERC, that is electrical rule check. One more important thing to mention here, sometimes you have to do the coding of DRC rules by yourself. For this, each tool have their own language. In open world, you may learn Tickle, that is tool command language, because some of the tools uses Tickle to code their DRC rules. You must have silicon fabrication process knowledge as a must-have fundamental for this stage, that is physical verification. EMIR checks are done on the layout and violations are mitigated by layout correction. I have already mentioned the EMIR tool names in previous digital and analog domains already. Finally, the chip goes for the tape out. We are done with this particular slide, so let's move on. So this is our series skeleton. We have so far covered this in last two episodes. In today's episode, we will cover this. So without any further delay, let's begin. IP design and characterization. Before beginning anything, I would like to talk about IP. The full form of IP is intellectual property. This is the dictionary meaning. In VLSI, IP means a self-sufficient design block which has finite number of inputs and outputs. There should be always a particular functionality associated with this design block. The purpose of the IP is to create once and use many times as required. I would like to explain the terminology characterization in VLSI. This is a process to do the electrical current, voltage, power variation and record the intended level of changes. This is done through VLSI EDA softwares meant for characterization purpose for various types of IPs. This oval represents the entire IP domain. Now, let us see what different types of IPs are designed in the VLSI domain. One thing I would like to mention before going any further, that is all the IP types that I am going to describe are designed by different teams inside a single company, that is IP vendor. Or IP vendor company may design few of the IP types based on people's expertise with them. When you apply for a job in IP vendor company, you may get allocated to one of the specific IP design team. You cannot be omnipresent in all of the IP design team. So you have to make a judicious choice when you enter into the IP design company, also known as IP vendor. Also, many IP companies put the exact IP domain in the job description. That will help you to understand the particular type of IP they are designing. The standard cell IPs are the most widely used IPs. Why? Because these are the heart of any digital design like ASIC or SoC design. Also, most of the time, the characterization jobs are for standard cell characterization. Generally, the standard cell IP library contains huge number of total cells. Here, I would like to mention that each design block are called cell in any part of the IP design. Now, the standard cells have collection of unit logic cells, sequential cells, combinational cells, power management cells, special type of cells like pillar cells, decap cells, A2D, D2A cells, and ECO cells, etc. There exists PVT variation, that is process temperature voltage variation, threshold voltage variation, metal track variation in the standard cell library. One more thing, based on the process, there could be FinFET or CMOS variation. Another type of variation comes from the bulk or SY substrate that on which the IP is getting designed, thus containing all the variation. This is the largest big fat IP category in the entire IP domain. Next, we talk about the memory IPs. Memory is an essential part of any electronic gadgets in recent time. Memory is found in CPU cache, PC RAM, smartphone, internal and external memory, smart home appliances, pen drive, SSD hard drive, smartwatch, etc. Thus, we have memory everywhere. Various needs, as mentioned just now, require memory IPs broadly categorized as SRAM, DRAM, eNVM, that is non-volatile memory, flash, and VRAM, that is battery powered RAM. Generally, memory design has two parts: unit memory cell design and memory array design. Sometimes, like in case of SRAM, we have another part called memory compiler design. These are the design part, and the characterization part is also there. Sometimes it is called the memory verification too. Next, we have analog IP. These are pure analog design blocks with single function. A few examples of analog IPs are DC-DC IP, PLL IP, audio IP, DLL IP, etc. The PLL IP is used as clock source. The DC-DC IP is used in power bank. Audio IPs are used in the audio unit of any electronic gadget. Many other analog IPs you may find during your search. The next type of IP is SerDes, which stands for serializer and deserializer. These IPs convert parallel data into serial data and vice versa. These are like hotcakes nowadays due to the popularity of its usage in handheld devices. Nowadays, a lot of companies investing a huge manpower in this IP sector. So, this is a prime standalone IP which speaks for itself. The next set of very popular IPs are USB, MIPI, and PHY. These are mixed signal IPs like SerDes. USB IPs are like hotcake because we are having so many plug-and-play devices around us which use the USB port for data exchange. And you also know that there are so many USB port variation exist nowadays due to the variety of USB dependent devices like printer, scanner, smartphone, OTG devices, OTG pen drive, USB headphone, microphone, USB webcam, personal MP3 player, iPods, and so many such devices. MIPI and PHY are very much popular like the USB also. The next kind of IP is the I/O pad IP. You know that any silicon chip needs the I/O interface to talk and listen with the external circuitry. This I/O part of any silicon chip is contributed by the I/O pad IPs. Thus, this is a IP that every silicon chip needs. We are done with this particular slide, so let's move on. IP design views and characterization. IPs are basically small design blocks. So if it is a digital IP or an analog IP or an AMS IP, we follow the respective design methods as described in previous episodes. One thing I would like to emphasize that IP level, the unit cell layout is always handmade, that is handcrafted. This is because these are the building blocks. Here lies the difference from the previously mentioned all design flows. Now let us see what all the views are corresponding skill sets you need to have. When you are designing any digital IP, the unit cell must have a Verilog, system Verilog or VHDL representation of the unit cell. For analog IP, the HDL changes to Verilog A or sometimes Verilog AMS based on the end application. So, working at this stage requires the mentioned HDL knowledge. The timing library characterization is the one of the most popular, also you can call famous, job title. For standard cells, we call this as standard cell characterization. At this stage, dynamic timing analysis is performed using Liberate or Silicon Smart EDA softwares for the standard cells library. The dynamic timing analysis at the unit cell level is a set of spice simulation from which the rise time, fall time, delay, slew, load, all these data are collected and put in Liberty format, that is .lib. For IPs other than standard cell, the choice of the characterization tool may be a pure spice, a fast spice, or an accelerated spice. Few names are HSpice, Vector, Eldo, HSim, FineSim, UltraSim, CustomSim. Among these, you may learn the pure spice by yourself, but fast spice or accelerated spice are available only inside the VLSI industry. The layout at any IP unit cell is handcrafted. Here, at the unit cell level, you design everything in form of diffusion layer, poly, substrate, metal 1, via 1, metal 2, etc. The 5 formats that you deal with are .OA and GDS2. For this, you use either of the tools such as Virtuoso or Custom Compiler from the major EDA tool vendors. So, you must develop your skills on these tools. One free tool you may use to practice the basics is Magic Layout. The schematic is an essential part of the analog IP design. Here, you have a library of active and passive components from which you can drag and drop components in your workspace. Then, you interconnect them with wire at power source and ground. Then, you add analysis type like AC, DC or transients as per the application of the IP. Thus, you can create and test unit cells of analog IP. You need to have skill set of Virtuoso or Custom Compiler schematic capture tool. You can also have the taste of schematic based free tool LT-Spice for your practice. The parasitic extraction view, that is PEX view, consists of the RCCC, that is resistance, capacitance and coupling capacitance extracted netlist from the layout. For this stage, your layout must be DRC and LVS lean. You must know StarRC or QRC extraction tools as per the skill set. There is another layout format view called LeftDev. This view is for Cadence PNR tools only. Skill set is same as mentioned in the layout section pictorially just above this block. Spice or CDL is another view of the analog IPs. The skill sets are same as the schematic capture as you can see pictorially above and discussed few minutes back. Physical verification view are there in the IPs. These could be for EMIR or DRC or ERC or LVS. At this stage, you must have tool knowledge such as ICV, PVS, Caliber, Volta-Phi, CustomSim, EMIR, etc. In summary, I can say that IPs are developed as per the need of the technological progress. We have discussed many types of IP in this episode, but I can bet that you will find many innovations in the IP domain in upcoming years. We are done with this slide, so let's move on. In this series, we have answered the question by following series skeleton as displayed in the screen. So far, we have covered this, and this. Today, we will talk about this and this. So, without any further delay, let's begin. Domains inside test chip unit. In any of the domains discussed so far, we make a design to achieve a target functionality. This could be a digital design or a analog design or a mixed signal design. Each design have to fulfill its design specification in the software as well as in the silicon. For this purpose, the test chip also known as a prototype chip. Even for a IP design units, we can have test chips constituted out of the designed IPs. Thus, the figure of merit of the IPs can be verified on the silicon and compared against the simulation values. This oval represents the entire domain of test chips. Now, let us visit the different pockets where the test chip units exist in VLSI. In the RTN to GDS to flow, we make SoC, and this flow is generally called the ASIC design flow. Here, we make multi-million gate chips. The toolkits that are used in the design process are standardized through the toolkit regression checks. Here, in this regression, for each technology node, we have small test chip designs included already. These test chips are designed once and reused again and again. Now, these designs are upgraded technologically with advancement of either the technology node progression or the novel fabrication process improvement. The design process of the test chips are same as the SoC design flow discussed in earlier episodes. Schematic to GDS to flow is for the analog designs. Here, the designs are itself smaller than the ASIC chips. Hence, the test chips are comparatively smaller. The test chip designs are also reused over technology node progression. The distinctiveness of the analog designs are that there will be many innovations to improve functionality, leakage, power, and timing. The innovations are a kind of unique in analog design domain. All of these innovations are tested in the software and finally in the silicon to test chips. The skill set needed here is same as the analog design flow discussed in earlier episodes. Full chip verification is applicable to all of the test chip domains captured in this slide. Here, we use robust simulators, both analog and digital, as applicable. The verification for analog, digital, and analog mixed signal are already discussed in previous respective episodes. The difference in that full chip verification is much more rigorous and time consuming. Hence, you have to be at the advanced level. This means you have to be seasoned with each verification of respective domain, and you must know advanced features and methods of verification EDA softwares. DFT is very important subdomain. Here, all the DFT related tool knowledge are essential and mandatory. Here, at the test chip level, you have to be thorough in DFT troubleshoot. In DFT, to troubleshoot any kind of issues from software to silicon. Post-silicon validation is to deal with the silicon chip. We have the physical chip here and have to use all the physical measuring system in the breadboard level. Your knowledge of instrumentation and handling advanced equipments is necessary. Practical knowledge is preferred over theoretical knowledge. This is similar to the practical sessions that you do with your equipments such as CRO, etc. Here, more advanced laboratory equipment such as from Agilent Technologies and many other vendors are needed. Here in this domain, the practical sessions from your college days are leveraged. Preparing the silicon report is the final domain. Here, you list out software versus silicon results across various dies and PPTs. Generally, the figure of merit are captured in silicon report. This is the highest experience level. You cannot join as a fresher at this age. This requires a lot of on-job experience over multiple years. The reason why so is the silicon report goes to the customer and it has a direct impact on the business relationship of a existing customer or winning a completely new customer. We are done with this particular slide, so let's move on. VLSI CAD domain. This oval represents the entire CAD domain. Often CAD is also known as EDA automation domain as per the application. This CAD automation is omnipresent across all the domains discussed so far. For this domain, scripting knowledge of Perl, Bash, SQL, Python and Ruby are needed. Also, you have to have knowledge of the end tools, that is EDA softwares for the respective domain. You have to have strong written and spoken communication skills because you have to frequently chat with different designers of a same team or across multiple teams. If the domain has interdependency, then you have to have cross-domain knowledge. Professional extrovertness is much needed in such CAD role. Now, let us focus one by one into all of the subdomains. The front-end CAD requires to create or maintain the design flow from RTL or schematic up to just before the layout in both analog or digital design. The required tool knowledge is already discussed in all of the previous episodes. Sometimes your knowledge of each design stage could face a challenge during solution of a bug. So you have to be very upkeep in learning all the hot and happening things that your CAD automation covers. The DFT CAD requires the automation to provide smooth DFT inspections over a given design. As said earlier, your knowledge must be up to date for domain tool or hot and happening things. The PNR CAD involves the proper layouting mechanism automation. In digital or analog, both you must know SQL as per the automation of the layouting steps. For Cadence PNR, you may need to learn skill language, which is Cadence's proprietary language and not like the open language ASIC. For PNR, your domain knowledge of semiconductor fabrication technology must be crystal clear. You must brush up stick diagram concept before entering this domain. The physical verification CAD plays a very important role in either analog or digital design. You must have theoretical knowledge of EMIR, DRC, LVS, antenna rule check for this particular domain. As per the end tools, you must know ICV, PVS, caliber from the major EDA vendors. As a CAD person, you may have to code the DRC, ERC or EMIR rules as per the language of the respective tools just mentioned now. For this, you have to understand the design rule document coming from the foundry and to be found inside the PDK. Your regular scripting knowledge of Perl, Bash, SQL, etc. are also needed for wiring things up. IP view CAD is applicable for the IP vendor companies and may be applicable for a design house who extend views with respect to various multiple EDA softwares that they use. In the IP view CAD, you need to maintain consistency across various views of a single unit IP through CAD automation checks. The various views may be from various design stages. Again, each stage have spatial variation for multiple vendor tools. For one single vendor, the views may vary from 2 to 3 EDA tool release versions. So, such overall complex distribution can only be maintained through automation. This automation may report missing view of a particular IP of any kind. The IP quality check of and quality assurance is maintained through IP QA/QC CAD. Here, the purpose of the automation is to check the view compatibility with respect to the specific EDA software. This automation ensures the complex IP view distribution to be QC passed for each of their respective tool. Also, for IP vendor, the automation must ensure the quality standard specified by the foundry technology node. For this, you have to have top to bottom domain knowledge of the specific IP type, that is either analog or digital or analog mixed signal. Design environment CAD is to provide easy environment for the designer so that he or she don't have to bother about the changes in the EDA softwares. Such design environment CAD provides the designer a plug-and-play interface for the designer. The CAD cockpit provides designer an easy interface which may have complex steps in the background developed and maintained by the CAD engineer. CLI to GUI CAD requires GUI automation knowledge such as TickleTK, Cadencil, Qt GUI, Python GUI. Here the GUI means GUI. Here the CAD engineer designs a GUI for the designer who operates the GUI. The GUI is designed and maintained in such a way that it may translate the GUI instructions into command line instruction in the background, then run the tool and finally display the results back to the GUI. So thus it saves a lot of effort for the designer. This impacts the turnaround time of the design from start to finish. Here you need the domain knowledge also. Before concluding, I would like to mention few more skill set that you need to have anywhere in the CAD domain. These are concurrent version system CVS or its latest avatar SVN. These are version control systems for the automation script repositories. You also have to have knowledge of the Univa Grid Engine abbreviated as UGE or IBM Load Sharing Facility abbreviated as LSF to judiciously use the computational resources, that is end machines. Sometimes you may have to recreate a fault or error by your own before solving the problem. Root cause analysis is a much needed troubleshooting skill for the CAD domain. Sometimes a front-end CAD engineer may have to talk to a back-end CAD engineer or IP CAD engineer and vice versa all along. You must be well equipped to open support tickets against tool issues in the respective EDA software support portal. That's all for today. We are done with this particular slide. So let's move on.
In today's episode, we will discuss about different job roles and their scope of work in VLSI. If you are a fresher or planning to join the domain, this video will help you. So let's get into the topic. First, design engineer. Design engineer is a job role where the engineer designs a brand new circuit for an upcoming chip or modifies an existing design already realized in form of a published chip. In VLSI, we design fresh chips as per need. Hence, we have to start a design from scratch. Here, the need of a design engineer come into the picture. Design engineer can work at associate chip level, sub-chip or subsystem level or IP level. Now, let's discuss about the different design engineer roles we usually see across entire VLSI arena. First, RTL design engineer. They design a particular digital circuit using HDL. They take help of state machine to capture and incorporate any novel digital design. The job role may include the responsibilities like designing the functions of modules of the system on chip as per input and output specification, optimizing the design to achieve best power performance and area, implementation and verification of high performance and low power clock distribution network and building block. Second in the list is physical design engineer. Physical design engineer has to work on the chip layout. The work may start from floor planning and may go up to engineering change order. Third, IP level design engineer. Design at the very block level with basic functionalities. The nature of design could be digital, analog or digital plus analog, that is mixed signal. Number 4 is the digital design engineer or architect. Such engineers are responsible for defining and realizing digital functions on IP, subsystem or IC level based on required specification. Number 5, analog design engineer. If the IP and the design is analog one, then we call them analog design engineer. Different types of memory design comes under analog design. Second type of position is verification engineer. Well, after design engineer post, let's understand about verification engineer. When a design is made by a design engineer, it has to get verified for its intended functionality with all sorts of possible permutation and combination of input and control signal values. Hence, the need of a verification engineer comes into the picture. Depending on nature of the circuit and methodology of verification, we can further divide job roles into digital verification, analog verification, AMS verification, and DFT. Verification engineers design and implement testing procedures to determine if products work as intended. These skilled engineers are responsible for creating the initial product verification methodology, selecting the testing environments and developing testing plans. First, digital verification. The digital verification engineer operates before the FPGA, ASIC or SoC production phase. He works with the design teams, that is FPGA engineers or microelectronic engineers, etc. in order to verify their designs, that is IP, subsystem or system. The verification can be realized at different abstraction level. Until unit blocks verification. The verification can be made at the RTL blocks level. Thus, we test all the functionalities of an IP through simulations. Verification at the subsystem level. The verification can also be realized at the subsystem level, including several IP. Then we check all their functionalities and their integration in the subsystem. Third is top level verification. Once the RTL design is verified at the unit level, we can integrate it at the top level. Required skill for this kind of position includes skill in ASIC or FPGA verification, basic knowledge in design techniques Verilog or VHDL, a good knowledge of simulation flow, good understanding in scripting, Python, Perl, Bash, etc. Second type of verification is analog verification. Analog verification is a methodology for performing functional verification on analog mixed signal and RF integrated circuits and system on chip. Third is analog mixed signal verification, a single verification environment combining both analog and digital solvers that can be used to functionally verify at the desired level of accuracy using their option or both digital and analog engines. Metric-driven verification to analog components in a mixed signal design. Number 4 is DFT. Above mentioned 3 verifications are pre-production, whereas DFT is done after production of the chip. During the design process, extra logic is put in the design which actually used to do post-production testing. The purpose of DFT is to validate or verify that the end product does not contain any manufacturing defects. After verification engineers, next in the list is PD or physical design engineer. Moving to physical design means moving from abstract level to silicon levels. So actually all the engineers look to the design through lens of silicon. Physical design or backend starts after synthesis and includes step up to sign off. So basically floor planning, placement and routing, timing or STA, power budgeting and area implementation, ECO task, that is timing and functional ECOs to address functional bugs and timing violation, physical verification like LVS, DRC, etc., noise analysis, electromigration, antenna checks, all this comes under job role of a PD engineer. Obviously, it should be a big team to perform and complete all these complex works. Required technical and professional expertise for a PD engineer includes good knowledge and hands-on experience in physical design methodology, which includes logic synthesis, placement, clock tree synthesis, routing. It's expected that the candidate should be knowledgeable in physical verification, that is LVS, DRC, etc., noise analysis, power analysis, and electromigration. Good knowledge and hands-on experience in static timing analysis, good understanding of timing constraints, automation skills in Perl, skill, or TICL are expected. Strong background of ASIC physical design, that is flow planning, PNR, extraction, ion drop analysis, timing and signal integrity, closure, etc. Extensive experience and detailed knowledge in cadence and synopsis or magma tools are much preferred. Expertise in scripting languages such as Perl, TICL, strong physical verification skill set, etc. are required. After physical design engineer, next is application engineer. Application engineer works at the customer interface. They both take care internal and external customers. It doesn't mean to meet the customer face to face always. There is a continuous communication via mail or ticketing system. They take care of customer needs. Let's understand this from perspective of a EDA tool vendor. An EDA tool company sell its products or tools to many design houses. Every company wants to make their tool bug-free, although all tools have some bug. When the engineers from design team of some other company face any issue regarding the tool, they get back to the EDA tool vendor and application engineer from EDA company look into the issues. Then the application engineer take R&D team in the loop and give solution to the customer. This is basically post-sale position. In some cases, application engineer post is pre-sale position and their job role includes visit to customer campus. In such visit, actually they meet new teams, try to understand if there is any requirement where their EDA tool can fit. If a FAE can take up any lead and convert it into sale, then the matter goes to account manager and sales executives. This job role requires communication skills, including written, verbal, through WebEx, Zoom, or Google Meet. Field application engineer, corporate application engineer, application consultant are some popular designation of application engineers. The job title depends on companies. This kind of job role gives you satisfaction of solving problem, high stress of handling demanding customers, glamour of traveling, and obviously you will get amazing experience of people interface. Fifth job role is CAD engineer. CAD engineers are expert in CAD tool and they develop flows that integrate multiple tools, creating a rather seamless environment for other engineers to use, develops and applies computer-aided design, software engineering methods, theories, and research techniques in the investigation and solution of technical problems. Assessing architecture and hardware limitation, plans technical projects in the design and development of CAD software, defines and selects new approaches and implementation of CAD software engineering application and design specification and parameters. They develop routines and utility programs also. Prepares design specifications, analysis, and recommendations for presentation and approval, may specify materials, equipment, and supplies required for completion of projects, and may evaluate vendor capabilities to provide required products or services. Required technical and professional expertise like good knowledge of scripting languages like Python, Tcl, Perl, exposure to C, C++ or other functional programming languages, experience in different commercial tools, good understanding in VLSI domain, familiarity with standard software engineering practices for version control, configuration management, testing, root cause analysis, and quality assurance. Teamwork, communication, and problem-solving skills, in-depth knowledge in data structure, algorithms, and optimizations. For CAD engineer, it is advisable to gather as much as domain knowledge possible in the area of working. Sixth in the list is characterization engineer. There can be various types of characterization in the entire VLSI arena. At the very basic point, characterization means to list out the electrical properties and or associated physical properties associated with a circuit under concern. Now, by the nature of the circuit, whether it's digital, analog, I/O, or memory, the definition of respective job role is defined. For the characterization, there are generally industry standard simulation tools are there. If you are going for such a job role, you have to learn respective EDA software. For standard cell characterization, Cadence, Liberate, or Synopsys, Silicon Smart are most popular to EDA tools. For memory characterization, whether you are designing a RAM or ROM or NVMe or any other memory, generally there are a lot of custom scripts combined with professional EDA tools which will be given to you. For such characterization jobs, strong fundamental knowledge of the respective circuit is required. Seventh job role is silicon test chip engineer. Test chip is a functional miniature prototype of the ASIC chip under concern, or the test chip could be a test vehicle to test various design IPs of a IP design house. The test chip engineer has to be a jack of all trades. He or she must know all the steps from RTL to GDS2, and hence the test chip engineer job role is challenging and highly rewarding. Eighth in the list is sign-off engineer. You might come across the name sign-off engineer. However, for you freshers, we would like to tell you that these positions are not for freshers. When you have at least 10 to 15 years of continuous experience, then only you can look towards this job. Well, we have discussed in a generic way about some popular job roles in VLSI. These are the very basic information, not in very much in-depth analysis.